Oh, like gross.
That's really interesting. That unit two is like separated.
Page 12. Yesterday, we talked about two minor topics. One was linear approximation, and the whole idea there is most of our efforts is just trying to find order pair from the function, guys. Slope from the derivative, point slope form. But the one thing that is different is that we follow linear approximation because we're inserting a decimal into the tangent line, into that tangent line equation. Okay, so we're back on page 12. Let's finish up on L'Hopital's rule, and then I want to talk about cylinders and how it's similar but yet different from cones, mostly different, and then we'll start our quiz review. Okay, so what we talked about with L'Hopital's rule is that so this is going back to unit 1. When we're evaluating the limit, we always just plug in the x value to see what we get, right? Are we getting a real number? Are we getting 0 over 0? Are we getting undefined, such as like 10 over 0, which means that there is a vertical asymptote? But whenever we get 0 over 0, we know that there is work that needs to be done still, right? And then we go through those methods. Is it factoring? Is it conjugate method? Is it complex fractions? And we have very specific ways of working through those different types of problems to get factors to cancel out so that we can reevaluate so that we can get to our real number limit. But with L'Hopital's rule, it kind of is a one-stop shop, because if we get 0 over 0, rather than having to deal with the problem individually and kind of categorize it under different steps, we can just find the derivative of the top and the derivative of the denominator, and that will just allow us to reevaluate and get down to a real number. So it's a lot a lot of students prefer this method, and it's also an important concept because sometimes problems are going to be set up in a way where the only way to get through it is going through L'Hopital's rule. But let me talk about what's important here with L'Hopital's rule is the condition. Okay, we cannot do L'Hopital's rule unless we're getting specifically 0 over 0 or infinity over infinity. Okay, those are both considered indeterminate form, but I'm going to focus on 0 over 0 because that's the one that L'Hopital's rule is going to be more helpful with. I'll talk about infinity over infinity in a second. But we saw from example 4, we always do the same thing for every limit problem. We always plug in that real number, okay, and we see what we get. If we get 0 over 0, great. We can either go through algebraic methods, or we can get it ready and apply L'Hopital's rule. So as soon as we go through our derivative process with L'Hopital's rule, we reevaluate because our end goal is to get down to a number. That number is a limit. Okay. But we have to be careful, like for example 5, if we skip the step of evaluating the limit first, and we try going through L'Hopital's rule, you may get 4/3, right? And that may be your answer, but the condition is not right for L'Hopital's rule, right? Unless we get 0 over 0, we cannot do L'Hopital's rule or infinity over infinity. In example 6, we saw that this is a messy rational function here, but if I insert it 2, I get 0 over 0, and that gives me the green light to do L'Hopital's rule once. Okay, so I find the derivative top, derivative of the bottom, but then as soon as I do that, I need to reevaluate. Okay, I don't want to keep finding the derivative until or unless there's another 0 over 0, which will give me a green light to then do L'Hopital's rule again. So sometimes students would see a problem and they'll just keep finding the derivative until it gets down to a constant, but that may not always be the case. So make sure that you're going through your procedure, right? You get 0 over 0, do L'Hopital's rule once, but then as soon as you do that, reevaluate, okay? see where you're at. Okay, so let's go through a couple more examples, and I want to talk about what happens if it's limit approaching infinity. Okay, but right now we're dealing with real numbers. First things first. Okay, what's the first thing that we do? Plug in, right? So that is not going to change. Your first step is going to be the same as it was in unit 1. Okay, you got to plug in to see what's going on. So 5 goes in for x. What do we get? Okay, yeah, 25 minus 10 is 15. Denominator, we get 0. Okay, what does that mean? Undefined. Okay, limit does not exist. Now, if there was a one-sided limit, we would dig a little further and we would involve decimals. But here, the limit doesn't exist. We know there's a vertical asymptote. We do not find the derivative, right? We don't do L'Hopital's rule because the condition is not right for it. All right, let's look at example 8. Limit as x approaches 0, 1 over 5x plus 2, minus 1/2 all over x. All right, first things first. Plug in 0. Okay. And what do we get? All right, 1/2 minus 1/2 is 0. Top is 0, denominator 0. So, we could go through complex fraction, finding common denominators, but we're going to practice using L'Hopital's rule. But before we find the derivative, we do need to get our numerator a little bit cleaned up. What we can do is we can push that 5x plus 2 to the numerator, and then we can make it go through chain rule. We can bring that entire 5x plus 2 to the numerator, put the parentheses around it, raise it to negative 1 power. Okay, so now my numerator is set up nice and ready for the derivative. Okay, so chain rule says outside's derivative times inside's derivative. So outside is my parentheses to negative 1. Inside is the 5x plus 2. All right, so what's parentheses to the negative 1's derivative? Yep, negative 1 parentheses raised to the negative 2nd. What goes inside here? 5x plus 2. So we took care of outside's derivative. Let's move on to the inside. 5x plus 2 becomes 5. Good. Keep going. Negative 1/2 goes to a 0. So I'll just leave that out. Nothing to do with that 1/2. Okay, so we're done with the top. Okay, so now the denominator, we do a derivative separately. X becomes 1. Okay. Now, usually we don't do this, right? Normally we can't just say, oh, numerator's derivative, denominator's derivative, and that's my derivative function. That is quotient rule, right? But here, we're specifically doing the derivative top and bottom, we're not trying to reach the derivative function. We're just using the derivative feature to arrive at these limits answer that we're looking for. Okay, I'm running out of room here. I'm going to use the space that I have for 7, since it didn't take a lot of room. I'm going to do a little cleanup, but eventually I'm going to have to reevaluate. Right? I don't want to leave my limit in this unfinished form. I'm trying to get to a number. I still have to reevaluate. Okay, so I'm going to push this parentheses down to the denominator. The negative 1 and 5 will be up top. My exponent is going to turn positive. Okay, reevaluate. And we're hoping that initially it was a 0 over 0. After L'Hopital's rule, we're hoping that this will turn it into a real number. So negative 5 up top. Denominator gives us 2 squared, right? 0 in for x. 0 plus 2 is 2. 2 squared is 4. That's a real number, so we stop. That's our limit. Questions?
What happens to 5x?
Say it again. What happens to
5x and 5x plus 2 squared. What's that?
we're just reevaluating. So if I insert a 0 in for x, that becomes 0. 0 plus 2 is 2. 2 squared is 4. Yeah, so yeah, I didn't show all the steps there. I was just kind of plugging it. Yeah.
If we had 0 over 0 again, we could do that.
Good. Right. So if we get 0 over 0 again, then we can do derivative again. We can do L'Hopital's rule again, okay? But we don't want to just keep cycling through a problem without first double checking that, okay, do I need to do L'Hopital's rule again? If I do, then I should be getting a 0/0 before I apply that process. Okay, what do you notice about 9 through 11 that's different? Infinity, okay. Approaching infinity. Now, you could also do L'Hopital's rule with infinity. So if I plug in infinity, I would get infinity over infinity, and I can do L'Hopital's rule, derivative, reevaluate. But my preference is, I don't think it's worth the effort to go through L'Hopital's rule, because with infinity, I think it's just faster to just compare degrees, right? That's just a quick way. There's no need to find a derivative. Whatever the degrees are, we can get to our answer really quickly, right? So as a reminder, if my numerator degree is less than my denominator, then my limit is simply 0, right? If my numerator is the same as my denominator degree, then it's just the ratio of the coefficients. And then if my numerator is greater than my denominator, then I'm dealing with either plus or minus infinity, and this is where we test, 100 or negative 100 to see which direction it's going to. So I think that's faster and that's familiar. I don't think L'Hopital's rule is as useful for infinity. I mean, it works, but it feels like it's feels like it's more effort than needed. So I like it for real numbers, and also on the AP exam, they kind of sometimes design a problem where you're having to apply L'Hopital's rule. But when it comes to infinity, I just go back to the old rules that we have. We just compare degrees. It's a lot faster. So let's just go through the old rules instead. So limit as approach infinity, we have to switch gears. We don't plug anything in. We just compare degrees. Okay, so comparing numerator and denominator, which has a higher degree? Denominator, so this is just what? 0. So I think it's not worth the effort with L'Hopital's rule. Okay, number 10. Infinity, so we compare degrees. What do you notice? Numerator, so there's only 2 options, right? It's either positive or negative infinity. And we test, right? It's either 100 or negative 100, but this x value is headed towards a positive 100. So I'll just test positive 100. I don't care about the value, I just care about the sign. Numerator will obviously give me positive. Denominator, 2 times 100 minus 5, that's also positive. So positive over positive is positive. Okay, number 11 is also infinity. What do you notice when you compare degrees? The same. So just take the ratio. The ratio is just simply 3 over negative 2, negative 3/2. Okay, if we can turn back to page 8. Okay, so this is the last kind of new thing that I want to go over before we look at the review. And that is dealing with cylinders. We haven't talked about cylinders yet. But so let's take some time doing that. We're going to use this space for number 5 to kind of go through some things here. Now, a lot of students, I feel, get thrown off with cones and cylinders. I think the reason why is because the formulas look so similar. So I want to kind of show that this distinction there. See how similar they are, right? They both have pi, r squared, h. And I think because of that, a lot of us want to apply the same things that we did for cones, like similar triangles, setting up proportions and ratios, but we don't need to do that with cylinders. Okay, and I want to talk about and convince you that cylinders are a lot easier, a lot faster to work through than cones. But a lot of students make mistakes with cylinders because we spent so much time going through cones. It's just natural to just want to apply those things that we learned to cylinders. But let me just show some distinction here. Okay, so this problem, these problems are all similar in the sense that there's, some a container with liquid or some something inside where that's either increasing, water being poured in or water being drained. So let's talk about the radius and height between these two different shapes. Okay, so let's say in this problem, the coffee is being drained. It's being removed from this container. So as water level is changing or dropping, what's happening to the height? Is the height changing? Yes, height's changing. Okay, so let's say we have a cylinder, a cone container, and let's say water is being drained out of it. Is the height changing? Yes. Okay, so heights are both changing in these. Okay, now let's talk about the radius. So imagine the water level dropping. Is the radius changing? No. Okay. Let's talk about cones here. As the water level is dropping, is the radius changing? Yes. So that's the big distinction here. Here, the radius needs to be held as a variable because it is changing. We can't just insert a number and expect that number to stay throughout the entire problem because that's not the case. But here, the radius is constant. So do we need to hold on to that variable if we know what the radius is? No. So that's going to make the problem a lot easier. As soon as we know what the radius is, we're going to insert that in, and we can just go directly into finding the derivative. We don't have to go through and find one variable in terms of the other, set up proportions. And also, there's no triangles here, right? So we don't want to do anything with triangles. Even though sometimes problem provides you information like as if it's providing it for you for cones to try to see if you're going to be tempted into setting it up using cones. And a lot of times with cylinders, you're going to get unrelated information that's just not needed for the problem. So I think in that sense, it kind of makes the problem harder, even though it's easier because we're so used to thinking in terms of cones. Okay, so that's the big difference. Okay, as soon as you find the radius, that radius can be replaced. That radius is never going to change. It'll stay that value the whole way through. Okay. All right, so now let's look at number 5 and see if we can work through this. A coffee pot has the shape of a cylinder with a radius of 5 inches. So go ahead and mark that down. R equals 5. Let H be the depth of the coffee in the pot, measured in inches, where H is a function of time, measured in seconds, right, inches per second. The volume is changing at a rate of -5 pi root h in cubic inches per second. Okay. All right, just by reading this description, can we decide which variable that is talking about? dV dt. Okay, so V for volume. We see the word changing. We see the word rate. We see the word cubic inches per second. We know there's going to be a pairing of volume and time, so that must be dV dt. So put that to the side, dV dt. Okay, -5 pi root h. That makes sense because coffee is draining out of the container and that volume is decreasing. Find dH over dt. So that's our goal, to find dH dt. Okay, and here you see this very last sentence here. This means your answer will contain the variable h. Okay, so our final answer will contain h. All right, let's go to our cylinder formula. Okay, we said that the radius is constant, so I can just go ahead and replace r with what? 5, okay. What does that clean up to be? What's 5 squared? 25 pi h. So that's it. That's all it takes to get the function ready for the derivative, right? A lot faster than cones, but a lot of students struggle with this because they want to try to force a similar right triangle into this problem, which is just not part of this process. Okay, so now that we're here, we can find the derivative. Okay. With respect to time, okay, so v becomes d over dt. 25 pi stays. It's attached to a variable. And h becomes dh dt. Okay, we have everything that we need, right? dv dt is negative 5 pi root h. And we're looking for dh dt, so we're almost there at the answer. Right, takes half the time that cones do. Okay, divide both sides by. Reduce, reduce. They say that h will be in our answer, so that's fine. Pi's cancel out, the 5 and 25 cancels out, so I'm left with negative root h over 5. Okay, what's our unit of measure? Height, yep, height is a one-dimensional unit, so inches per second. All right, any questions there with 6? Okay, try number 7. And keep in mind that this is still a cylinder. And a lot of times with cylinders, they are trying to see if you will be tempted into doing something with cones. And because of that, you're going to have some information that is just not needed. Okay, they're providing you more information than you need. I mean, some of this information is relevant for cones, but it's not relevant for cylinders. So see if you can identify what those are, and you're going to avoid having to do anything with ratios, anything with similar triangles. Okay, so try that. I'll go through them. I'll go through each step after we try it. Yeah, sorry, this should be the height of the water inside the container, yeah. That's right, yeah, yeah, I think the wording is a little confusing here. Guys, it's the water that is changing, not the container itself. So it says at what rate is the height of the water inside the container changing? Sorry. The container itself is not changing, and it's the water inside the container. But yeah, we're looking for dHdt of the water, but the container is going to stay constant. Okay, so number 7, water's leaking out of the container at a rate of 2 cubic inches per hour. I know that's volume related, so cubic inches is volume, hour is time, dBdt. Water is leaking out, so we want that rate to be negative, so negative 2 cubic feet per hour. Okay, the container has a diameter of 8 inches. We know that what we really want is radius, because that's the formula that involves radius. So I can just split that in half and say that, okay, I know my radius is 4. Container has a height of 12 inches, but the water inside the container we're talking about half full, so when H is equal to 6. Okay. Now, looking at this equation here, what substitution can we make? The 4, right? The 4 can go in for that radius. That's the only thing that we want to replace, right? What information here is just not needed for this problem? Either of the heights, right? Doesn't matter what the height of the container is. It doesn't matter how much water there is in it, right? And we don't want to be tempted into plugging these values in for H, because if we lose H, we're not going to be able to find the derivative, and dHdt is just not going to show up for us, right? And so what that means is that that rate of height is not going to change, because it's just going to be a constant, because that radius is not changing. Okay, but we can build our volume equation with the constant radius in mind. So just with one substitution, we're ready for the derivative. You don't have to do any sort of radius over radius equals height over height, right? So in a sense, I think cylinders are easier and harder at the same time. It's easier algebraically and the stepwise, but it's also harder because we spend so much time with cones that our natural tendency is to bring in the steps for cones in for cylinders. So in that case, it kind of makes this problem harder than cones, because a lot of times I see students approach this from the cones perspective. They do cones perfectly, and they try to do the same thing here with cylinders. So in that sense, I see students miss cylinders more often than cones because of that misunderstanding. Okay, so now let's find the derivative, right? V becomes dV/dt. 16 pi stays, and H becomes dH/dt. So if you look at your derivative, there's no need for H's, right? All we need is dV/dt, and then we can quickly get to our answer. Okay, so dV/dt is -2. Notice again, pi is in the denominator. It needs to stay there, even after we reduce. What's a unit for height? Inches per hour. All right, let's go to our test review packet. All right, does anybody still need to look at number 7? Okay, so first page and second page, these are both old FRQ problems that've been given on in previous AP exams and a good practice for us here. Okay, so let's read number 1 here. A circle is inscribed in the square as shown. So here's my circle inscribed inside the square. The circumference of the circle is increasing at a constant rate of 6 inches per second, sorry, inches per minute. Can we just read this and decide what that's referring to? Or what variable can we call that? Right, circumference is c, rate of change is dc dt, and positive or negative. Positive, we see the word increase. Okay. Okay, as the circle expands, the square expands with it. So the circle, the square is going to kind of move in the same way that the circle does, so that this condition is still met. It's still tangent to the square is still tangent to the circle at these 4 points. Okay, so part A says find the rate at which the perimeter of the square is increasing. So what are we looking for? dp over dt. But before we can do that, we got to build the perimeter equation first. Okay, so we need to talk about that for a moment. We need to build the equation first before that dp dt can come out. Okay, how do we define perimeter? Adding up all the length of the sides, right? Adding up length of sides. Now, I think sometimes we want to maybe introduce a new variable and call it x. But if we do that, then we're not taking advantage of what's given to us. And the hint is that they already gave us a variable to work with, and that variable is r. Is there a way for us to build the perimeter using just that variable r? Okay, what do you know about the side length in terms of r? Right, r is half the length of the square, a side of the square, so that's 2r. Each of the sides is 2r. We add all that up. P equals AR, right? So we're taking advantage of the fact that, we don't want to introduce a new variable when there's already a variable that is going to connect us between the square and the circle. All right, so that's the hard part there, trying to see that connection. But then after this, we can find the derivative, and we can involve the next step here. So now we can find the derivative, right? P equals 8r. Time is our independent variable. All right, so P becomes, right, 8r becomes
8.
Yeah. Okay, we still have a little bit of work ahead of us because we don't have dr dt, but we have dc dt. So is there a way for us to get from dc dt to dr dt, and what will we need to build? Yeah, we have our circumference formula, right? And what can we do with that circumference? Find the what? Derivative, right? If the derivative comes out, then the CTT shows up, the RDT shows up. We can find that link and we can plug one in and solve for the other. Okay, so we have C equals 2 pi r. Find the derivative here, C becomes the C dt. 2 pi stays, and R becomes dr dt. Okay, our end goal is to figure out what dr dt is so that we can find dp dt. So now that we have this second derivative equation, we can take this 6 inches per minute, put it in for dc dt. That can free us up to get to dr dt. That'll be the final piece that we need to get to our variable that we're ultimately looking for. Okay. Divide the 2 pi over. Again, we see so many times, right, that pi is in the denominator. We want to keep it there, okay, for the entirety of the problem. Okay, so reduce. 6 over 2 is 3. Pi is still in the bottom. Okay, so we have dr dt. All right, but we're not quite there yet. Our final step, we're looking for dp dt, so we can replace dr dt with 3 over pi. I get 24 over pi. Okay, what's our unit of measure? Good. So perimeter is still a one-dimensional unit, right? It's only area and volume that has something different. Everything else is one-dimensional. So, yeah, inches per minute. Okay, part B. Okay, at the instant when the area of the circle is 25 pi square inches, and we know that this shape is continually increasing, but there's a moment in time when the area of the circle is exactly 25 pi inches. So I'll put that to the side. Find the rate of increase in the area enclosed between the circle and the square. So we're talking about this region here. Now we know that that is not a geometric shape. So we don't know the formula for that region, but maybe we can use the regions that we do have to create an area formula for that. And how can I find the area of this using the shapes that's available to us? Right, so if I take the square and if I subtract the circle, I'm left with those corner regions. Right, so let's build our formula now. So I know that area of the region that I'm looking for. Area of the region is equal to the area of the square minus the area of the circle. So let's build the area of the square and area of a circle. Now, area of a square, again, we want to take advantage of the variable that's already been provided for us. So what's the area of the square? Yeah, close. Yeah, 2r squared, but if we clean that up, what does that become? Yeah, distribute that 2 through, right, and make it 4r squared. Okay. Okay. Area of a circle, formula is pi r squared. Okay, so area of the region is just, sorry, 4r squared minus pi r squared. Okay, so we have to build the equation before we can find the derivative. But now that we have our equation, you can jump into our derivative step. A becomes the dt. 4r squared becomes 8r dt minus pi to r dr dt. Now the dr dt we can import from part A, 3 over pi, so that works out nicely. But we're still missing the radius of this ever-changing circle or this region here. And do we have something to help us get to the radius?
Sure.
It gave us the area of the circles at the moment in time, so we can therefore find the radius at that moment in time. Set those equal to each other, solve for r, and that r can be used for this derivative. Okay, so we can replace r with 5, replace dr dt from what we gather from part A. That's still applicable. And then in the end, we don't have to clean up our answer. We just try to get it as, whatever we can do to it. You don't have to find common denominators. But finally, what's the unit of measure? Area is in terms of square inches per minute. Okay. So replace r with 5, replace dr dt with 3 over pi. And then just try to do some cleanup here. 8 times 5 is 40, 40 times 3 is 120, so 120 over pi. Here, I just got the pi's to cancel out because one's in the numerator, one's in the denominator. The 2 and 5 is 10, 10 times 3 is 30. Okay, let's see if we can get through a part of number 2. So number 2 on the back, we have two shapes here. We have a cone up top and a cylinder below. Now, for number 2, they are breaking the problem up into nice steps. We're just going to focus on similar triangles, get that cone equation ready, and then the derivative will follow. Okay. Sorry, we're skipping number 2. Sorry, we're skipping number 2. We're going to 3. Okay, skip number 2, back page, number 3. Okay, as shown in the figure, water is draining from a conical tank with a height of 12 feet and a diameter of 8 feet into a cylindrical tank with that as a base with the area 400 pi. The depth is changing at a rate of h minus 12. Part A just says, write the equation for the volume of water in the cone tank as a function of h. Okay, so it's already kind of telling us, focus on h, and after you do similar triangles, you're going to solve in terms of h. So let's go ahead and set this up. We know with cones, we're going to be dealing with similar triangles. So the problem already tells us that we want to get our function in terms of h, which means that I want the r to disappear. If I want the r to disappear, I want to solve for r so I can find the replacement for r. I'm going to divide by 12. You take your r for part A, you're going to start building our volume equation. Take that h over 3, insert it into the r of your equation. Get it cleaned up. That will be for part A. Part A is not asking for the derivative, it just wants you to create a cleaned up version for the volume so that when it gets to part B, it's ready to go with the derivative step. So we like to put all the numbers together, all the coefficients together, and then merge all the variables together. So the pi, the 3, and 9, we can all put that together as pi over 27. Put the h squared and the h together, call it h cubed. All nice and ready for part B, which is the derivative. Okay, I'm running out of time here, but I just want to talk about something real quick. Next week, your quiz was initially scheduled for Tuesday. But I feel like it's good if we have an extra day. So the quiz will be on Wednesday, but we're tight on our schedule. We're not going to have an extra day of review. So I'm going to swap Tuesday and Wednesday. So Wednesday, we're going to start notes for 3.1. Obviously, it's not going to be on the quiz, but it buys you an extra day to review for your quiz. If there's time at the end of class on Tuesday, I'll try to bring in some more related rates review. Help session Monday morning and help session Wednesday morning. I'll send out a reminder this weekend. All right, come get your phones.